artist, yada yada. I do stuff on YouTube. Go check out my stuff on YouTube. More importantly, I'm here to talk to you about lerp smoothing. This is a really esoteric corner of game development, so it's not really super useful beyond that, but I just want to dive into it, because this has been my obsession for months now, and so I just want to share my obsession. That's basically what this is. OK, so what is lerp smoothing? This is something you might find in Unity forums or in various places of how do I smooth this motion? And then you're going to find someone who goes, oh, you can use lerp smoothing. Just write this small little function that'll just solve it for you. So lerp smoothing is a technique to make something smoothly follow something else. So here's a little bit of sample code. It's very simple. You have two things, A and B. They could be positions of objects. And then you have your update loop, so that runs once every frame. And in there, you just write A equals lerp, AB 0.01. It's a very simple line. You also don't have to use a lerp function. You can just write some math straight up like that as well. So it's a very easy function to implement. It's so easy to remember, and it gives you really beautiful results. And all it really does is it says move A 1% closer to B. That's it. That's all it does. And so when you use it in practice, this is what it might look like. So we have two sliders here. B is our target value, and then A is going to be the value that's animating over time. So you can see that it's kind of smoothly following this dot, right? And it's kind of nice that we can just kind of move it around, and it just follows responsively to it. It's not like a rigid easing function or anything. We can just dynamically move this around, which is pretty cool. So it's really, really useful. And you can see it in motion. So in this case, again, the red dot is following the blue dot. And again, it has this smoothing function, which makes it take this really, really smooth path forward, which I think is beautiful. I think it's kind of mesmerizing, I think. While working on these slides, I was just sitting staring at this sometimes while thinking about other stuff. It was really nice. All right. However, lerp smoothing has a problem. And the problem is that it's broken. It doesn't work. You might think it works. It looks great when you run it on your computer, but let's say you made a game, or rather, you made this lerp smoothing experience that you want to share with your friends. And so you send it to your friend and another friend, and then you want your friends to play this experience, right? But this is what happens. They get two different experiences. And I mean, usually that's not what you want when you're making a game. Generally, you want them to behave the same, but for some reason, they don't. There's some discrepancy here. And so the reason for this is because your first friend is running at a cinematic 24 frames per second. And your second friend is running at 120 frames per second. And so that's why they get these hugely disparate outcomes in behavior. So here's another example. So this is the same thing. The yellow one is 24 FPS, and the red one is 120 FPS, and they're trying to follow the blue target. And ideally, the yellow one and the red one, they should be the same. They should overlap, but they don't. And so this phenomenon is known as frame rate dependence. In other words, it's when a behavior depends on frame rate. So if you change the frame rate, you change the behavior. So, all right, let's first just before we try to solve lerp smoothing and fix that, let's just take a look at a more simple example, linear motion. So in linear motion, you can write that in an update loop. So you have some speed value. It's 0.01 in this case. And then on every frame, we increase a value by speed. OK, so this basically says increase A by 0.01 once every frame. So we send this to our friends again, and they try this. And so this looks fine. This looks linear, right? It's linear motion. Sorry. But you send it to your second friend. And for your second friend, it just goes 5 times as fast. And you can imagine, if this is your player character, like this is the movement speed of your character, it feels a little bit unfair that your second friend gets a much faster character, you know? And then you send it to a third friend, and their friend is like, their computer is just doing something else in the background. And so here, their frame rate is not even consistent. And so in this case, like the first two, they have a discrepancy, sure. But the third one, that's not even linear motion. That's just non-linear motion, because it's like starting and stopping and like accelerating all the time, all over the place. So this is bad, and we want to try to avoid this from happening. OK, so just zooming out a little bit, what's happening is that the code a plus equals speed runs once every frame. So the speed it reads here, the speed value, has to be in units of meters per frame. But we want to specify speed in meters per second. Like that's how we measure like velocity of like real-life objects, right? Not meters per frame. We don't care how quickly something moves per frame, right? But the problem is that the computer cares a lot about that. So our goal now is going to be to find a conversion factor, x, to convert meters per second into meters per frame. So there's kind of a fun little trick we can do with something called dimensional analysis. I only recently learned about this, so I hope there's no like actual mathematician in the audience. But basically, the idea is that you kind of treat your units as algebraic objects. So we can write this equation where we have meters per seconds, the units, times a conversion factor, equals meters per frame. So if we want to find this conversion factor x, all we have to do is solve this equation for x. In other words, we multiply both sides by seconds. So now we have meter seconds divided by frames. And then we divide both sides by meters. So now we have meter seconds divided by meter frames. And the meters cancel out. And so our conversion factor is in units of seconds per frame. Now, you might recognize seconds per frame. It's not quite the thing you're familiar with, which is probably frames per second. In other words, frames per second is the inverse of seconds per frame. So this inverse also goes under a different name. It's known as delta time. And delta time is really just the time since the last frame, or the duration of the current frame. So for example, if you are running a game at 10 frames per second, that means that you have a delta time of 0.1 seconds per frame. And so that is then the delta time in that simulation. OK, so this is our conversion factor. We just need to multiply it by delta time in order to convert our speed from meters per second into meters per frame, which is, again, what the computer wanted. And then I put my water bottle somewhere else. So I'm just going to open the water bottle that's here, and I hope that's OK. OK. So all we have to do now, it's kind of underwhelming, but all we have to do is multiply by delta time. Like, that's it. And so we give it to our friends again. Our first friend is running it, and it's linear, as we expect. And now our second friend has the same experience. Now they have the same speed per second, and that's what we care about. And even our third friend, who has the most inconsistent computer ever, like, they also have a pretty close experience to the other two. Like, sure, it's a little bit choppy because we can't add frames where the computer literally can't catch up, but it's about as close as we can get. All right. And so here's what it looks like before we fix linear motion. So again, these two dots are following the blue dot. And this is just with linear motion. And so if we add our fix of multiplying by delta time, then immediately they get the same speed, and they start converging on the same answer to this simulation. The code for this looks a little bit complicated, and the only reason for that is because we want to make sure that if we're following a target, we don't want to surpass or like jump past to the target. Because again, our constraint here is that we want to run at a consistent speed, But if we get close to our target with consistent speed, we're going to like zigzag really quickly when we're close, and that's not good. And so we're going to let this one just snap to the destination if we overshoot it. So if you want to write this function for like vectors instead of numbers, then all you need to change really is to make a and b vectors, and then abs v is just going to be the magnitude of v, and sine of v is just going to be the normalizing v. So these are kind of the equivalent functions just for one-dimensional values, I guess. OK, so but this talk was about lerp smoothing. It's not about linear motion. With linear motion, you kind of get this like very robotic, like consistent speed, which might be what you want in some cases. If you want to make a robotic arm animation or whatever, that is what you want. But in our case, we want something that looks a little bit more smooth. Like there's something really calming about lerp smoothing. It's very like nice the way that it settles in a very calm manner. And it's somehow also responsive. It doesn't feel sluggish, which is a really nice property of lerp smoothing. OK, so how do we solve frame rate independence for lerp smoothing? That's going to be the goal now. So first, we need to understand lerp. So lerp stands for linear interpolation. And it's a very simple formula. All it really does is has these three parameters, a, b, and t. And the formula is 1 minus t times a plus t times b. That's it. There's nothing more to lerp than that. And so you can kind of interpret it as a being the start value, b is the end value, and then t is kind of a fraction or a percentage, usually between 0 and 1, to blend between a and b. And so to illustrate this blending, here we have the values a and b on this slider right here. And then in the middle, you can see the results of the lerp function. And then we have the t value last. And so if I change this t value, you can see that the result of the lerp function changes along with it. And so if t is 0, it's stuck at a. And if t is 1, it's stuck at b. And then anything in between is a linear blend between these two values. So no matter where a and b is, the t value is going to say, how far between a and b do we want to move as a fraction of that distance? So that's what this is. And in this case, I'm not just blending the position, but I'm also blending the colors. So if you might be able to see that this one is red now, and then it slowly blends towards purple, and then slowly towards like this cyan blue color. So you can kind of use lerp for almost anything. Anything that you can multiply and add, you can use lerp for. So you can use it for colors, positions, angles, quaternions, whatever. All right, so lerp smoothing. So this might be a little counterintuitive, because lerp is a linear blend, but lerp smoothing has a non-linear behavior. Like it had a curve to it, right? And so lerp smoothing is kind of a special case where the first parameter a is given a new value, which is the result of the lerp function. So the lerp function gives us a new value, and then that's going to be the input for the next iteration of this function. So let's just like simulate it a little bit here. So we have a lerp function. We start with a equals 1, and we're going to blend towards the value 2. And we have a t value of 0.5, which means halfway. That's 50%. And so halfway between 1 and 2, we have 1.5. And then the next time we run it, we're going to use 1.5 instead of using 1. And so now we're going to go halfway between 1.5 and 2. And so then we get 1.75, and so on. So now we do 1.75 here, and you can see how this continues, right? This is how lerp smoothing operates, basically. And notably, the step between all of these values decreases over time. It becomes smaller and smaller and smaller. And so that's why we have this nonlinear behavior, because the percentage of halfway becomes shorter and shorter. OK, so just to demonstrate this a little bit now, we have a and b as usual. But now the middle is going to show each iteration of this. So this is just the first iteration. We start at the value a. And then n is going to be the frame number n. And so now if we jump one frame, you can see that it's jumped a certain percentage toward b. And then if we continue to drag this, you can see that it jumps closer and closer and closer for each frame. But it jumps quickly in the beginning, and then it slows down at the very end. And then the t value in this case is going to control kind of how quickly it makes that jump. So 0.5 would be halfway on every iteration, so halfway between each of the remaining distances. And so if it's 0, it can't move anywhere. If it's 1, it teleports to the target immediately. And so that's kind of the functioning of the lerp smooth. OK. So this is kind of like Zeno's paradox, right? So I don't know. I don't remember the exact details, and I don't respect Zeno enough to look it up. But the basic idea is that if you want to move towards some target, you need to get halfway before you get there. And then if you want to get even closer, you need to get halfway of that remaining distance. And so if you count up the number of halfways there are until you reach your destination, that's an infinite number of halfways, right? And so Zeno has a bunch of paradoxes related to this, in which Zeno said, it is impossible to traverse an infinite number of things in a finite time. OK, so Zeno's paradox, we can just simulate this. Like we can just run a starting value of 1. This is the same interpolation we did earlier. So we have a equals lerp from a to 2, and we're going to jump halfway on every iteration. OK, so we get the same values as before. 1, 1.5, 1.75, and so on. And here you can definitely see that it's slowing down, right? Like, it's not reaching the value of 2. It's just it's taking so many frames. And so, yeah, basically the idea is that no matter what, you will never reach the target value. Except you actually will in this case. So Zeno, he didn't know that it actually just takes 53 iterations to reach the target. And that's because Zeno just failed to consider binary floating point formats. So very, very weird that he missed that fact. OK. All right. So one way to think about this, or one way to visualize this, is to just draw a graph. So this is the same thing we looked at before, but now we're just visualizing it where the vertical axis is the value, horizontal axis is the frame number. So each dot is a single frame in our simulation. So I'm renaming the third parameter now to f. So that's going to stand for lerp factor. All right, so if we change f, you can see that the curve of this changes when we tweak this value. And of course, we're interpolating between specific values of a and b. So right in this case, we just started with a at 1, and then b was at 0. So in a lot of these demonstrations, I'm just going to put b at 0 and a at 1 because it just looks nicer and it's easier to reason about. But this is effectively what the lerp smoothing is doing over time. OK. Oh, sorry, I'm poking the mic. I have hair in my mouth. OK, so if we then visualize this over time with different frame rates, we can just clearly see the problem with lerp smoothing. You have it right here. We have 2 different frame rates, 24 FPS here in blue, and then 120 FPS in red. And you can just see that these are entirely different motions when we map them over time. So now the horizontal axis is time, not frames. And this kind of sucks. We don't want this to happen. This is bad. OK. So the question we might ask then is, what shape is this? It's a curve, but which kind? What's happening here? And so for linear motion, where we had a plus equals delta time times speed, it's relatively easy to just draw the connection of, the rate of change over frames is delta time times velocity, and then you can kind of translate that into a motion over time, which is, f of t is the starting position plus time times speed. And so that's just kind of the canonical, example of what derivatives even mean. So it's relatively easy to make that connection. But for lerp smoothing, it gets a little bit more complicated because we're starting out with this weird function where we're just assigning to one of the values that we're using in the function itself, and it feels like this Ouroboros situation. And so how do we go from lerp smoothing to a continuous function over time? That's the challenge now. OK, so how do we identify this? Well, we know that it's not a constant function. It's not a flat line. We know that it's not a linear function. But maybe it's a parabola. Maybe it's a polynomial. Maybe it's a hyperbola, where we divide by the time value. Maybe it's an exponential function. Maybe it's a power function. Maybe it's some trigonometric function, like some inverse hyperbolic cosecant. Who knows? There's so many things, right? And so let's see if we can identify this. So I think there are many approaches to doing this, but the one that I'm going to do is basically treating this as a recurrence relation. So in other words, we have a function over frames n. That's the one right here, function over n, not over time, where the initial value at frame 0 is a. And then the nth value of this function is going to be lerp from the previous value towards b with a lerp factor of f. And so, and again, the lerp function, there's nothing special about lerp. Lerp is just math, so we can replace the lerp with the math inside of the lerp function to just unpack that. Excuse me. All right. So this is a recurrence relation, and it's kind of like a recursive function. And so if we write out the first 4 frames, then we might be able to deduce a pattern here. So for the initial value, that's just a by definition. But for the next value, it's going to make use of the previous value here, f0, which is equal to a. And all of the frames ahead just work exactly the same way. They just use the previous value. And so what we can then do is that we can substitute f0 with a. Just plop it in there, because they're the same thing. F0 is the same thing as a. That's what equals means in math, right? That's why we can just replace things. And so we're just going to shove that in there. And then we do the same thing with f1. Excuse me. We do the same thing with f1, just shove all of this in here. And it's going to grow a little bit now. And then we do the same thing. And so now we have explicit formulas for each of these frames. We're no longer making use of the previous frame's value, because now we've kind of hard-coded them into each of these. But this doesn't actually solve the problem of working out that function over frames. But what we can do is we can pick one of these and then see if we can work out a pattern by simplifying them. So I'm going to take the third frame, which is f2, and then we're going to try to simplify that. So the goal now is to find f of n in order to get that continuous function, but we're going to do it specifically just for the second frame or third frame, f2, just to see if we can see a pattern. And immediately you can kind of see that we have 1 minus f as a recurring theme here, and so we can make kind of an educated guess that 1 minus f is going to be important to solving this. And so 1 minus f times a, we can break that out from this inner function. And then we get a times 1 minus f squared, because we're multiplying 1 minus f's together. And so I made this 2 yellow here, because I suspect that this is going to be the n when we solve f of n. And so then we might want to try to do the same thing for b over here. We want to try to create a 1 minus f to the power of 2. And so let's just first break out b, because we want that separate. And then we simplify the inner part of this equation. I don't trust these 2's to be this 2 over here, right? And so there's an image here later. It's spoilers. I'm sorry. And so OK, so now our goal is, can we convert this part into a 1 minus f squared? So 1 minus f squared, if we just expand that, 1 minus f squared is almost equal to this. It is a positive f squared minus 2f plus 1. And so what we can do to make it more similar is that we can negate the contents of this. But if we do that, we have to negate the outer part as well. So we just negate it. And so now we're one step closer. Now we want to add a 1 inside of here. But like any modification we do to this equation, we have to balance out with some other change. Otherwise, we change the meaning of this equation. So if we add a 1 in here, it's going to do minus b times 1, which means that we need to add b to compensate for adding a 1 in here. And so if we add a 1, we have to add plus b at the end to make sure that the equation is still the same thing as before. All right, and now 1 minus 2f plus f squared is equal to 1 minus f squared. And now we have a and b share a common factor of 1 minus f squared, so we can simplify once again. And now this is looking pretty good. Like, I'm satisfied with this. And this is the point where we might make an educated guess of like, OK, maybe we can just assume that this 2 is generalizable. Like, this might be the n that we're looking for. And I checked, and it is. So we solved it. There we go. And so, all right. So now we got that. That's good. So this is what it looks like over time. And again, now the x-axis is not time. It is frames. And this is what the function looks like. So it's no longer just discrete frames. Now we have a continuous function. Because, again, we can just shove in a non-integer value as the exponent, and then we get this nice curve to it. OK. I need more water. Oh, while I drink water, remember to think of questions, because there's going to be questions at the end, I think, unless I take too long to talk about this. I'm going to try to keep up to make sure there's space for questions. OK, so all right, so we started with this lerp function, a equals lerp abf. And then we worked out the continuous variant of that, in other words, the version that's not recursive. And the cool thing about this function is that we don't need to know the previous frame's value. That was the thing that's kind of annoying with the lerp smoothing, is that it's a recursive function. So the next step is to figure out the same function, but over time instead of frames. I'm going to make a little bit of a leap here, but if you consider time, if you have some number of frames, and you multiply that number of frames, n, by delta time, you get the total duration of all of those frames. And so the inverse relation also applies. So if we want to convert this from a function over frames n, we get a function over time if we replace n with time over delta time. Because if we slice up time into the size that the frames are, we get the number of frames out of it. I'm making some assumptions about the frame rate being consistent here, but ignore that, and everything is fine. OK, but this is still frame rate dependent. We haven't fixed any problem at all. We've just done some math, and that kind of sucks, right? But we did find the continuous function over time t. And that's a good first step. And so this is what it looks like if we map it for 30 FPS and 60 FPS. And again, we can see that there's a frame rate dependence here, because depending on frame rate, we get different curves. Again, not good. OK. So you might think, OK, so, well, if f is kind of like the fraction to move after 1 frame, is f times delta time the fraction to move after 1 second? So long story short, no. We can't just multiply by delta time. There's a very long story here that I couldn't fit into this talk, and is also the reason why Jonathan Blow blocked me on Twitter, because of a conversation about this. But anyway, long story. So OK, let's just try to think a little bit about what it is we're actually doing here. OK, so now we're showing our function over time. We're showing frames with dots. And we have our lerp factor f, and we have our delta time here. So we can change the frame rate now. So decreasing delta time is shrinking the size of each frame, which increases the frame rate. And so here we can very clearly see that the curve changes when we change frame rate. And that's, again, not what we want. And so what we're really dealing with here is that the constraint that we've set up for our system is that after one frame has passed, the remaining fraction should be f. That's the problem that is automatically solved by lerp smoothing. And so if we change delta time, in other words, change the frame rate, this coordinate is just moving horizontally. And so it can't have the same curve because we've forced it to not be the same curve. And so I think the big realization is that we actually do not care about where this curve is after one frame. Like, who cares? That doesn't matter. We just want the same shape, and we want to be able to control kind of the steepness of this curve, but we don't care about where exactly that is after one frame. In other words, f, we don't care about f. So maybe we can find some different way to parameterize this very same function by using something other than the remaining fraction after one frame. So we should try and maybe pick something that's consistent across frame rate, like 1 second. So we might say, after 1 second, I want there to be r remaining in this interval. So r is, again, a fraction, but now it's fraction remaining within this interval. So what we can then do is that we can sort of solve this for f. If this is going to be our new input value, so we input the value r, so r is a known value, and then f is going to be controlled by r. So f is going to be dependent on r. So we basically just, we don't care about f anymore. We just dump that, and now our new input value is going to be r. And so now the goal is we want to express f in terms of r. Because f can be whatever it wants to be, as long as it solves our constraint that after 1 second, there should be some specific fraction remaining. Right, OK, so f was the fraction traversed when time is at 1 frame into the future. But r is the fraction remaining when we're 1 second into it. OK, so this is the function we had before, when we solved it for the continuous function with the frame rate dependent version. And this we can actually use. OK, so this is the constraint that we now want to solve for. There's a lot happening at once here, but effectively what this says is that the function over time, that's what we have here, at 1 second, we want the fraction remaining to equal r. That's what this says in English. So because that's the constraint that we set up. That's what we want to happen. And this minus b divided by a minus b, some of you might recognize that as an inverse lerp, if you've ever used that. But it basically just converts this from an absolute coordinate into a fraction within the interval that we're in. So it turns it into a 0 to 1 value within that interval. OK. So we can then take this function and just unpack it. We just shove the function in there. And again, what used to be time is now going to be 1 second, because that's the moment we care about. And then we can simplify this. And obviously, we have some easy simplifications. We have plus b minus b, so that disappears. We have a minus b over a minus b, so that disappears as well. And so now we need to, again, we want to define f in terms of r. So we want to try to isolate f on its own side of this equation. So we can raise both sides to the power of delta time, which cancels out the left-hand side. And then we subtract 1 from both sides, and then we multiply both sides by -1. Now we have f equals 1 minus r to the power of delta time. OK, I need some more water. OK. So now what we can do is we had f in our old equation, right? But now we have this new relationship. We know that f is, again, exactly the same thing as 1 minus r to the power of delta time. So this f, we can just replace it with our newfound equation, right? So we shove that in there, and now we have 1 minus, in parentheses, 1 minus r to the power of delta time. This inside simplifies into r to the power of delta time. And then this delta time, you have something to the power of something else, and then to the power of something else. That delta time actually jumps up over here, and then we have delta time over delta time, which cancels out into 1. And then we end up with this function. And every time I do math and I get a result like this, I'm just like, no. This is too simple. I must have done something wrong. I must have accidentally canceled something out that I shouldn't have. Maybe I don't understand derivatives correctly, or I don't know. But let's put it to the test. So here we have the function, and now we have r as the input value to this function instead. And so now the question is, will the shape of this curve change if we change the frame rate? And it's actually kind of obvious when you look at this function that delta time is not even part of it. So of course, the curve is going to have the exact same shape when we change frame rate. And so now we've actually turned this into something that is frame rate independent. All right. But we're not quite there yet, because we haven't implemented this in code, right? We just have some math theory, And that's not enough. We need to make sure that it actually works. All right. So we need to get back to code. So how do we get back to code from this function? Because previously we had this per frame assignment in an update loop, but now we just have a function over time. But in our update loop, we don't have a time value that's just ever increasing, right? We don't know when some animation started, and that's kind of the whole point of lerp smoothing, that we don't need to know when it started. It can just dynamically follow the target, whenever, wherever, however, So how do we convert it back? And so this is where it gets a little bit tricky, but we can start by looking at the bad one, the one that is frame rate dependent. So if you consider what we're really doing, when we use this in code, is that A is really the previous frame's value. And the time that we're going to use is 1 frame into the future. And so that's really what we're sampling when we sample this in code. And so we just replace t with delta time. And so what happens then is that we get delta time over delta time, which simplifies to 1. And so the realization then is that this part right here is the remaining fraction after 1 frame. And that's exactly what the code is doing every frame. And so that's kind of so we can just take that and just directly translate that into code. So then we get a minus b times 1 minus f plus b, which just so happens to be exactly equal to lerp from a to b with factor f. And it's not a coincidence, because that's where we started, and then we worked our way here, and then now we've just gone backwards again. But now we need to do this with a fixed version, the good one. So OK, so now we have f of t equals a minus b times r to the power of t plus b. And then we look at this function 1 frame into the future, which is delta time. And then the same thing applies, because this equation has the same structure. So this part right here is just the remaining fraction after delta time has passed, after 1 frame. And so we can just take that directly and translate that into code, and we get a minus b times pow, which is the power function. So r to the power of delta time plus b. And of course, we can write this using a lerp if we want to. It's just that we have to do 1 minus, which is a little bit gross. I don't like that. So anyway, so there you have it. There we have some code. And now we just need to figure out, does it work? I don't know. Maybe it seems fine. So let's look at the broken version first. So this is shit, I fixed it. There we go. Let's look at the broken version first and ignore time. And so here's the broken one, right? It just has frame rates all the way up from 10 FPS to 110 FPS. Those are the transparent white ones, and you can see just how off they are, right? And so then the question is, of course, if we then apply our new method of using r instead of this lerp factor f, will it work? And now you've been spoiled, because I clicked it before it was visible, because my HTML skills are great. All right, and so look what happens to this animation now when I enable using this r function. they very quickly converge. Like, it doesn't even take that long. Like, now they are about as accurate as can get. Like, this is really, really good, right? Like, it runs even as far down as 10 FPS, which is a horrible frame rate. And even if I like try to abuse the actual R value that we're using of like moving it around and like changing it over time, and you can see that it's like still keeping up really well. It's really just the 10 FPS version that's not keeping up very well. And so basically, we fixed it. That is one way to fix it. And that's kind of neat, I think. That's the thing I wanted to share, I guess. But there's a little bit more we need to talk about. So I want to talk about half-life. Now, this is not half-life, which is very disappointing, I know. But I want to talk about something called decay. So let's say you have a set of dots, and each of these dots have an update loop, so it runs once every frame. And in this update loop, we have this condition that basically says there's a 3% chance that we will turn off this dot. That's it. That's what this does. So we have 9 dots, and on the right, I'm going to graph the number of dots in this box. And so I'm going to run this simulation. And so there we go. We have some sort of cliff, and then like a big house down here, a procedural cliff generator. Let's try it again, see what happens. There we go. Some more lumps. That one really wants to stay alive. And so there we go. This is kind of like random lumpy thing. But now, let's, instead of using 9 dots, I'm going to increase this to 1,024 dots. And now watch what happens. It's still completely random. I haven't like rigged this or anything. It's simulating live. It is just generating random numbers. And yet, it creates this extremely precise curve. It is a little bit wobbly, sure, but it is weirdly, weirdly similar to the curves that we've been looking at throughout this entire talk, right? And so this is actually the exact same process that we see in radioactive decay in real-world materials. There's a random chance that some particle will decay and eject from some material, and then we get this really interesting curve to how the number of particles changes over time in the source material. And so this can actually be computed, and the constant for this is usually denoted using a lambda. And it's the exponential decay constant. And in this case, it would be 3% divided by delta time, if we want to calculate the decay constant for this. And then the decay function itself that we use in the real world is a function over time that is e to the power of decay times time. So that is the exponential decay function. So this gives us a fraction of the original amount at time t. OK, so and we can also graph this in this chart. And so if we just draw that right there, you can see that if we run the simulation, it is super close to that line. Like, it's kind of weird that we just have this random process, and somehow it just wants to stick to that curve. And you can imagine when you have real-life materials, like actual radioactive isotopes in the real world, there's going to be a lot more atoms and molecules than 1,024. And so you can imagine how much more accurate this gets the more things you have. OK, so and this is the basis for like radiometric dating, by the way, for like carbon dating. If you want to know how old a fossil is, if it had like a material that formed at some point in time, because this curve is so predictable, that's why we can kind of work backwards to figure out when this material was formed, which I think is kind of cool. So what does this have to do with lerp smoothing? Well, so there's this really cool property in exponential functions where if you have a value a, you raise it to the power b, that is equal to if you replace a with c and then multiply the exponent by the c logarithm of a. And so you can kind of swap out the base of any like exponent like this. So just to take an example, if you have 8 to the power of b, and then we swap out the 8 with 2, then that's equal to 2 to the power of b times log 2 of 8. All right, my mouth is just a desert right now. OK, so and so this also applies to the number e. So we can just swap out any base with e. Oh yeah, the log 2 of 8, it happens to be 3, and so it's just equal to 2 to the power of 3b. So with e, we can replace a with e to the power of b times the natural logarithm of a. A natural logarithm is just another way to say log e. It just has a special name because it's really useful in math. OK, and e is just a number. Like e is a constant, sometimes known as Euler's number. I would say it's the most important number in all of math. It is ridiculously important and central to like everything, which is it's wild. Read about it. It's cool. If you want to calculate that number, you can just do 2 plus 1/2 plus 1/6 plus 1/24 plus 1/20, and just continue that sequence forever. And so that is the factorial sequence. So 1 over 2 factorial, 3 factorial, and so on. And you can kind of just write that as a single for loop if you want to. So just iterating from 0 and upwards. And then you just add all of those together. And so this is how to calculate e if you want to do that. Don't tell Zeno that you have to do an infinite number of calculations here. OK, so why do we care about all of this base swapping nonsense? Well, we worked out that we can have our function, and we can define it using the remainder after 1 second. So changing our remainder changes the shape of the curve. But we don't have to use specifically this constraint. We can use like a bunch of different other constraints. So for example, and here we go. This is half-life. This right here is half-life. It's not denoted using a lambda, which is very disappointing. But maybe science will fix that at some point. And I'm going to close whatever that is. All right, so this right here is half-life. And what half-life is like the remaining, or the time it takes for the original quantity to reach half of its original amount. So that's what half-life means. So that's a duration. But we can also define this using the exponential decay constant, the one that's actually used for radioactive material. Well, I guess half-life is as well, but the decay constant is also used for a bunch of other things. And the decay constant, in this case, represents the slope at the start of this curve, or specifically the negative slope, but who cares? Doesn't matter. All right, so a little summary. So we started out with this code that we ran per frame. And then we worked out that we could write this as a function over time. And the function over time fit the formula of b plus a minus b dot dot dot, as in times something. And that something happened to be 1 minus f to the power of t over delta time. And the important part here is that like if there is a delta time on the left-hand side in the function over time, your function is frame rate dependent. Delta time does not belong here. It should not be in the function over time at all. But then we worked out that we could use another function of just like, instead of using all of this, we could replace it with r to the power of time. And we could write that in code as this whole thing. And now that we know that we can swap out the bases and kind of use different ways of expressing this, there's actually alternate solutions for this that you can also use. So if you want to use half-life, you can do 2 to the power of negative time over half-life. And again, that's that in code. And you can also use the exponential decay constant. So you can use e to the power of negative decay times time. And so this is what that looks like in code. So math libraries pretty much always have POW. They pretty much always have EXP. Sometimes they have EXP2 as well, not always. But you can just use a POW function for that as well. But I'm going to warn all of you, because all of you are probably like, oh, cool, r to the power of time. That seems like the best one. It looks the simplest, so I'm going to use that. But do not use that. It is bad. And the reason for that is because the POW function happens to be very expensive, like ridiculously expensive, if you compare it to the exp function. The POW function, I think, is about 8 times as expensive as running exp. So don't use the POW function. You're just wasting processor cycles. So instead, if you want to do lerp smoothing, just do this. Use the decay constant. If you want to take a picture of anything in this talk, this is the slide. This is the only useful information I have, and so this is it. And of course, it's best to define a separate function, and then you use that function so that you know what you're doing, because lerp smoothing can look kind of esoteric in your code. And delta time is usually accessible pretty easily. In Unity, that's time.delta time. In Godot, it's an input to the process function called dt. And so you can just shove that in there. Just make sure you get your units correct, that you're matching, delta time should be in seconds and not milliseconds and so forth. But yeah, that's basically it. Thanks for coming.
Thank you. Thank you. Thank you. OK, thank you. We have time just for one question. And Paco Juan already told me that he wanted to do it, so.
It better be a good question. There's pressure now. This better be the best question.
You're putting me into an insane amount of pressure, man. But, well, thanks for the talk. It was amazing. I love the snail cat.
I like them, too. They're very good.
I'm probably going to steal it for you. I mean, it's amazing. So I was going to ask, there's a lot of, math concepts behind this, knowing, I can, cross this out with this other function, or substitute it with another thing, whatever. But I love that you have this part of just fucking around and find out. Mm-hmm. Saying, let's assume that this is like this. Let's check if it works and it does the trick. How much importance do you usually give this mentality while working in a day-to-day basis?
I think it depends on what your goals are. I think a lot of people are very focused on solving the problem just to solve another problem. Of say you're using lerp smoothing and your characters move incorrectly, and then in order to solve that, you Google how to solve it, and then you find this talk on YouTube, and then you copy and paste that, and then you're done, right? But I think for me, I really enjoy trying to get a full understanding of something. And so for me, I enjoy learning, why does it work? Why is this the solution to this? And I don't know, I guess I have the time to learn, and that's kind of nice. But again, it depends on, do you have time to learn that, or do you just want to continue with your life instead of getting stuck in math problems? But for me, I think it's a really good learning experience to jump into something like this. Also, I did have a few more things in my slides that I was going to do after questions, just a heads up. But yeah.
Thanks a lot.
Are we doing more questions, or should I wrap up?
Yeah, you should wrap up.
OK. OK, so it's all right. So can we switch to the slides, or did we nuke it? Oh boy, this got complicated. OK. Oh no. Now I feel bad. I should have warned them ahead of time. Oh no. There we go. OK, cool. I just wanted to add a few last things before I go. Just plug my stuff. This is my website. It's my URL. I'm very sorry. I just thought it was funny, because it was available, and I was I got it for some reason. Here's my email if you want to reach out. I have a Substack if you want to go on my mailing list, because social media is kind of weird these days, so mail it is, I guess. My YouTube channel, if you want to learn shader programming and math, just go there. I have a Patreon as well, and a Twitter. Yeah, so this is my business card. I don't have business cards, so if you want to have my business card, you need to take a business card of this. So OK, and then I have 2 bonus slides. Can I do the bonus slides? OK, bonus, hell yeah. OK, so, wait, what? OK. So we kind of did the dumb solution to this, and I think the dumb solution is kind of nice because it's more intuitive. But there's another way to solve this problem, which is this is a mouthful, but it's an autonomous first-order differential equation. So if we want to properly solve lerp smoothing, we would set up a differential equation where this is our original lerp smoothing. And then we translate that into a change per frame, or like a derivative, which means we subtract the current value, and then we get the change. And so y here is an unknown function that starts at a. And solving this differential equation takes us directly to the exponential decay answer. But solving differential equations is complicated, and so I just didn't really cover that much here. But that's another way of solving it, which is basically like answering the question of what happens if we set our frame rates to infinity, basically, like shrinking down our delta time to 0. And then the second thing is that this actually relates to spring physics. So if we expand our differential equation to include the acceleration, and then we can parameterize it, we get a really cool behavior where this is kind of like decay, and you can see that we have this dot animating by this curve. We can make it move really slowly as well, and we have this little animation. But the really cool thing about this is that we can make it underdamped, and then we get this spring motion. And again, this is not an easing function. That's the cool part about this, is that we don't need to know when this started in order to have this behavior. So if we solve this spring physics equation, we can get something that can just simulate each frame, and we don't need to be aware of when it started and how long it should go for. And that's why it's called an autonomous differential equation, because we don't need to be aware of what time it is. And that's why it works. That's it. That's all of my bonus slides. So if you have any questions for me, please just come up to me during the conference. You're going to be like, oh, no, I don't want to, like, she looks busy or whatever. Like, ignore that. And then just come up to me, and that makes me feel validated and special, and that's important to me. And so don't be afraid to come up and ask any questions if you have any. Yeah, that's it.
Next up is Anissa Sanusi. But